Yes, welcome back, everyone. I think I will turn this over to Daniel to field questions about the problem sets, Q&A, and anything else you want to talk about.
Okay, sure. Well, I think it's best if I turn this over to anybody who has any questions from the audience. That could be on what we covered in the lectures or about the problem sets. Anything goes. So please feel free to go ahead.
I have a question. This is maybe a silly question, but during the lecture, you mentioned that the requirement that the sum over the alpha index over all cross operators of k dagger alpha k alpha needed to equal the identity so that density matrices still have trace 1 after the map. Is that specific condition, it obviously guarantees that condition, but does the reverse direction make sense, right? Is it well justified that that is the condition to impose that the trace is preserved at 1?
So you're asking if it's necessary and sufficient, and actually that is one of the problems in the problem sets. So I will leave it to you to figure it out. It's indeed, it's not at all obvious that it's necessary. Right? It's clearly sufficient to preserve the trace of the density matrix. Yes, Berta, do you remember which problem it is specifically? Has it come up in the discussion?
So yes, this is problem 312.
So I also see, sorry, I see that Anders Peterson has asked, where are the problems? I'm sorry that wasn't made clear, but the problems are embedded in the lecture notes. Okay, so that's where you need to look for them, inside the lecture notes. Go ahead.
Mm-hmm. Right, so in problem 3.1.2, you're asked to evaluate the reverse of the condition of whether or not trace preservation implies the cross operator condition that the sum over alpha of k alpha dagger k alpha is equal to I. Right, and this can be a bit of a question of semantics, but this does turn out to be the case when you do require trace preservation to hold for all density matrices. Then it becomes a linear algebraic exercise to show that the normalization condition holds for the cross operators. However, it's not necessarily the case if you only assume it for specific, if you only assume it to hold for specific states. Then you can find a counterexample for the normalization condition.
Yeah, and the reasonable perspective is probably the one where you want to make sure that this holds for all density matrices. We don't want to single out any particular states, and so with that in mind, it is both necessary and sufficient.
Thank you.
I have a question. I was able to start reading your Lymphatic equation notes. I was wondering if you could maybe just give a little bit about the big picture of the equation and what it allows us to describe.
Okay. Sure. So let me actually grab this opportunity to maybe take 5 minutes to do that systematically. Okay. Okay. So the Lymphatic equation is an equation that we get when we ask ourselves whether there is something that's equivalent to a Schrödinger type equation for an open system. So, you know, the Schrödinger equation is a differential equation, right? So psi dot is minus I h psi. And now you want to know, is there something like that for density matrix, right? So can I say rho dot is something, let's call it L, acting on rho. Now, what is this L that generates the dynamics of the density matrix? Just like here, we know that this gives us the solution. Psi of t is u of t psi of 0. And we know that the most general dynamics we can have in the open system case is given by the Krauss operator sum representation. So we can ask whether there is a differential equation that has status similar to the Schrödinger equation. And that's called the master equation. In general, when you have this differential equation that generates the dynamics. Now, the master equation that gives rise to the operator sum representation, to a CP map, this with completely general Krauss operators, that's a pretty advanced topic. If you want to do this in complete generality, if you want to reproduce the operator sum representation, but and so I wasn't going to cover that. That's called the Nakajima-Zwanzig equation, which you can read about somewhere else. Nakajima-Zwanzig would be this, such that it generates the operator sum representation. But we can ask a simpler question, and that is, what if we just wanted to get a constant in time generator? This is the generator. L is the generator, just like the Hamiltonian is the generator of the unitary evolution. What if we wanted to get a constant in time generator L, and one that has in addition, has the property of generating a CP map, right? Like here. And the answer to that is the Lindblad equation. And so it turns out that you can always, well, not always, sorry, you can derive a differential equation for rho, and it has this form. First of all, it has the Liouville von Neumann term, right? That's the one that we already saw. But then there's an additional piece, and it has this general form. There are some rates here, gamma alpha, and then there are so-called Lindblad operators, L alpha, rho, L alpha dagger, and then minus a half the anti-commutator of L alpha dagger, L alpha with rho. And the anti-commutator between any two operators is just AB plus BA. So this is called the Lindblad equation. These gamma alphas, they're all non-negative. And in the lecture notes, you'll see a derivation of this equation, which starts from the operator sum representation. And basically, it's an attempt to find the Krauss operators such that rho at dt is approximated to first order. So dropping all the dt squared and higher terms. So if you just ask yourself, well, what is the differential equation that gives me the lowest order, that is up to order dt, time evolution, you plug this into the Krauss operator sum representation, and you will find that this can be described by a CP map, provided that you pick the Krauss operators as, let's say, K0, the first Krauss operator, minus I, a Hermitian operator, which you can identify as Hamiltonian, and then plus, let's say, minus 1/2 gamma alpha, L alpha, delta alpha. And all the other, this is times dt. And all the other operators, K alpha, they are of the form square root gamma alpha, L alpha, square root of dt. The square root of dt may seem strange, but it's there because when you have cross operators acting from the left and from the right, then the square root dt squared becomes just a dt. These L alphas, these are what we call the Limblad operators, and at this level, they are completely general. We can relate them back to the Hamiltonian and all that through the general expression we have for the Krauss operators. But again, it turns out that if you do this first order in time expansion for rho, find a CP map that will give you such an expansion, dropping all the higher order terms. These are the Krauss operators that you find, and then when you rearrange things, you find that you can arrive at this Limblad equation. And this Limblad equation, there's one important assumption that goes into it. The assumption is that not only do we assume this is true for dt, we assume that the same is true for all t. So in fact, we're saying not only is this expansion true at between 0 and dt, now we're going to assume that the very same expansion is true between t and t plus dt. And so essentially, we generalize to this times dt with the same cross operators. And this going from from 0 to dt to t plus dt, in other words, saying that it's true for all times, that these are the cross operators, that's the Markovian assumption, which is central to deriving the Limblad equation. The Markovian assumption says that the cross operators are time independent. Right? They are, in general, they're time dependent, but here you see they're time independent. And so dropping that time dependence is equivalent to saying that the BAF is constantly resetting. It has the same Krauss operators at any given time, has the same Krauss operators. So it's resetting. In other words, it has no memory. That's the Markovian assumption. And so this Markovianity is a defining feature of the Limblad equation. And then this equation is one that you can solve for some simple examples, and actually you can solve it quite generally. And if we wanted to, for example, take the dephasing problem that we studied. So dephasing, we had it over there. What we said was, let's say that we have Krauss operators such that the Krauss map phi rho is p rho plus 1 minus p 0 z like this. There's a Limblad equation which gives the exact same type of map. And the Limblad operators, actually there's just one. It's sigma z. And there's one rate, these gamma alphas, these are rates. They have units of 1 over time, so they're rates. There's one rate, let's call it gamma. And the Limblad equation, in this case, let's set the Hamiltonian to 0 for simplicity. So let's plug that into the Limblad equation, right? So rho dot is now, there's no sum over alpha because there's just one operator. There's one gamma here. And then I said that L alpha z, rho z minus 1/2. Now it's z squared, which is identity with rho. All right, so what is this? If this z squared is identity, so you have identity times rho plus rho times identity, that's twice rho. So this is just rho. So this Lymphatic equation is simply this. Gamma z rho z minus rho. And this is a simple equation you can solve for a qubit. And so it's a good exercise to do that. And if you solve it, what you'll find is that rho has the same, actually, let's write it in terms of the block vector. So the block vector, V, is Vx of 0 e to the minus 2 gamma t. Same for y. This is what you find when you solve this equation. And z, the z component, is constant. So what you see is that the block vector has x and y components that decay like e to the minus 2 gamma t. This is typical of Markovian dynamics. We have exponential decay. And if you recall, the block vector solution of this map was that Vx prime was 2p minus 1 Vx, the original, right? So let's call it Vx0. And let's call this now Vx of t, the one at the end of the map. And same for y. And if you recall, for z, it was constant. The block vector along z was constant. So you can now identify 2p minus 1 with this e to the minus 2 gamma t. It tells you that this probability that we were talking about earlier in the context of the Krauss map, we can give it a dynamical interpretation. This probability, 2p minus 1, is actually e to the 2 minus gamma t. All right, so the Lymphatic equation gives us a time-dependent perspective, whereas the Krauss representation just gives us a map. You start at time 0, and then you go to some later time, and it doesn't tell you what happens in between, in some sense. And in terms of the Lymphatic equation, we get the full trajectory. What happens at any given point in time? That's the nice thing about having a differential equation like this, as opposed to a map. All right, so that's the general picture. This is an example, and there are many more examples we can work out for that. Does that help a little bit?
That was really helpful. Thank you.
Okay. Are there other questions or comments? Any feedback you guys would like to provide? That would also be nice to know.
Can you please go over again the spontaneous emission problem and maybe explaining it a little bit further?
Sure. Let me go back there, and you can tell me what about it you'd like to see explained in more detail. This is pretty much it.
Yeah, I would like the physics around the problem. We know that, for instance, if we have hydrogen, we would have a spontaneous emission if we put it in one of the higher energy states, right? Mm-hmm. So I just kind of want to have the physical picture of this problem here. That wasn't that clear for me.
Yeah, so I have to say that the theory, the way that I described it, at this level, it's pretty phenomenological, right? So you have to do a lot of work to go from the hydrogen atom to a description that is compatible with the Krauss operators and so on. But it's totally doable, right? Because we know how to compute the Krauss operators. If you remember, we had that expression with the partial matrix element and so on of the unitary. So in principle, you can from first principles compute the Krauss operators for spontaneous emission. What you would do is you would write down the Hamiltonian that couples, let's say it's an atom in a cavity to the electromagnetic field. You'd have to quantize the field, second quantize it, and write that Hamiltonian, compute the unitary, take those partial matrix element, and you could compute the cross operators, right? So that is totally doable. It's an excellent exercise to try to do that. Here we are taking a giant shortcut, right? And we're just saying, let's forget a lot of the details, and let's summarize everything in terms of this probability of emission, P. Right? And the picture is, it's phenomenological, but it's also very simple. So we imagine that we have a two-level system with a ground state and an excited state. And all we're saying is that the probability that you go from the excited state 1 to the ground state 0, that probability is P. Right? And that defines a cross operator for us. Is that cross operator clear to you? Why that describes emission from 1 to 0?
Yes, that part is clear. It is mostly like the negative probability part that is confusing me a little bit.
The negative probability, where do you see negative probability?
No, you said like that we needed to account for the second term for K0.
This one.
Right? Yeah, that part is the one that's confusing me a little bit.
Yeah, no, you're right to be confused, because I really didn't do it justice. So if you forget about this part for a second, right, and let's say that you wrote down your second cross operator. Again, you know that there has to be one, otherwise the whole dynamic would be unitary, right? And that's not what's going on. So you know there has to be a second cross operator. And so the second cross operator, well, it's reasonable to say that it describes, because it's spontaneous emission, it describes that if you are in the 0 state, you stay in the 0 state. That is certainly true for a 0 temperature bath, or for a bath whose temperature is much smaller than the energy gap here. And it wouldn't have enough energy, the bath wouldn't have enough energy to excite the system back into the 1 state. So if you drop this term and you check the normalization condition, this one, you find that it's not satisfied. And you find that you can fix it by introducing this additional term. It just pops out of normalization. So now we can ask ourselves, so what does this extra term mean? And it's not obvious from the cross representation what it means, but it becomes more obvious when you write down the Lymphatic equation that gives rise to this process. And now that we talked about the Lymphatic equation, I can say what that Lymphatic equation is. So the Lymphatic equation that gives rise to this cross representation is a very simple one. It's one where you have a single rate again. So there's a single gamma, and there's a single cross operator. And that cross operator is simply the lowering operator, just like here. So it's this, or if you like, you can call it sigma minus. So it turns out that the Lymphatic equation with these parameters, gamma and just this lowering operator, precisely describes the same type of map. And you can relate the probability P to gamma, and you get something like P is e to the minus gamma t, or maybe it's 1 minus, let's think. So 1 minus, because when t goes to infinity, the probability that the event happened is 1. So this is the P that you're going to find. Okay, so now we know there's a Lymphatic equation that describes the very same process. Okay, now to really understand what this term is, because I still haven't explained it, there's a whole other part to the story which I haven't mentioned yet, but is very interesting, and it's called quantum trajectories. And the quantum trajectories is essentially a reinterpretation, as well as an algorithm, but it's a reinterpretation of the Lymphatic equation in terms of individual trajectories that the system undergoes as it's evolving as an open system. But each one of these trajectories now has a certain probability. So you almost think of it as like a path integral. And it turns out that in this language of quantum trajectories, this term finally starts to make sense. And it corresponds to essentially what this term describes are those trajectories where if you were to place a detector for this photon, right, that's emitted, you don't observe an emission event. So there are trajectories where you observe an emission event. If you observe an emission event, then you know that the system went down in energy from 1 to 0. But in some cases, your detector doesn't click, right? So a click means an emission happened. But sometimes the detector doesn't click. Well, what are you supposed to do with that information when your detector doesn't click? Well, I mean, if it didn't click, then either the system was already in the ground state, or it's in the excited state waiting to transition. And that's what this term actually means. This term actually, the interpretation is it corresponds to trajectories where the atom is in the excited state and hasn't yet emitted. So that's the honest answer about what it means.
Great, thank you. Now it's much better. Still, the details, of course, gonna be fuzzy,
Yeah.
but
I have a question.
Yeah.
If you just write some general Lindblad equation the way you did, is it always guaranteed that there will be some corresponding system bath Hamiltonian picture that will give you this simplified equation?
Yes, because so again, these are the cross operators. Right, so this K0 and K alpha, and here alpha is a general index. Alpha is 1, ... as many Lindblad operators as necessary. If you assume that these are the cross operators and that they are always the same, they are, in other words, they're time independent, then the Krauss representation gives you a Lindblad equation with precisely this form. Okay. Now, in turn, you can always construct Krauss operators from the prescription that we know, right? The prescription that K alpha is square root lambda nu matrix element. So you can always find a bath state, meaning these mu and u, and a unitary, which look like this. So which give Krauss operators that look like this. In fact, there's not a unique way to do that. There are infinitely many system bath interactions and bath states that will all end up looking exactly like this. So there's always a way to find an underlying system bath model which gives rise to any given Lindblad equation, which I think is what you asked.
Yes. Okay. Thank you.
Professor Lida, could you please give some general directions about non-Markovian dynamics?
Yeah. Non-Markovian dynamics is, first of all, the Krauss representation is in general non-Markovian. Right? You get Markovian dynamics provided that you have Krauss operators that look like this. But if your Krauss operators don't look like this, then the map that is being described is generally non-Markovian. Basically, non-Markovian dynamics, a rough way to think about it is to understand it as rather than having a fixed generator here, there is now a time-dependent generator, right? One that depends on time. That's not completely not a completely general statement, because I can make the Hamiltonian time-dependent, right? And it would still look like this. But but Hamiltonian dynamics is Markovian. So the exact answer about non-Markovian dynamics is actually fairly complicated, and there are a lot of debates in the literature as to how to quantify non-Markovianity exactly, what is an appropriate measure. But here's what I can say. The general consensus about non-Markovianity is that it involves an information backflow from the bath into the system. If the bath has no memory, okay, so that's the Markovian case. And what we mean exactly by memory is something that we quantify. Right? Let's just say that what we mean by that is that the state of the bath at any given time is independent of the state it was in before. That's roughly what we mean by no memory. So if the bath has no memory, then there can be no information backflow into the system, because whatever happened was already forgotten. So non-Markovianity has to do with this information backflow. When it's there, then there's non-Markovianity. When it's not there, in other words, when the bath forgets, then the dynamics is Markovian. I mean, the topic is vast technically, and lots of different equations that people have written down for non-Markovian dynamics. The most general one is just the cross representation, because that's the most general case that we have, up to the assumption of factorized initial position.
Okay, thank you.
Can I just keep ask a following question on this? So you're saying the general consensus of non-Markovian derives from that has a memory or information backflow from the batch to the system. Sorry, am I speaking clearly, or?
It's a little hard to hear you, but I'm doing my best. Yeah.
Yeah. I was just recapitulating that you're saying a non-Markovian process, generally consensus is the information backflow from the batch to the system. Seems that we're assuming that the system cannot have its own memory, but the memory is entirely in the batch. Is that what? Why is the system not having its own memory? In this definition of non-Markovian, you're saying the batch has the memory. And when the batch has no memory, the dynamic in general is Markovian. But in that sense, why can't the system have its own memory? That its dynamic depends on its previous dynamic. Isn't that also a sort of the non-Markovian process?
Yeah. Well. Okay. So the property of being Markovian is ultimately a property that we associate with the dynamics of the system, right? So I think I understand where your question is coming from. So let me try to be more technically precise about it. Let's go this way. So, for example, with the Lymphatic equation, we have an equation that looks like this. Right? And so the solution of this equation is simply rho of t is e to this L, same LT, acting on rho of 0. Right? And we can call this is some super operator. Let's call it lambda of t, capital lambda. And you see that this has the property that this is true for it, right? So this is sometimes called a one-parameter semigroup. And a lot of people are happy with the identification of Markovian dynamics with this. If you need more than one parameter to describe the dynamics, All right, so let's say that actually we had a dynamics which was described by a different type of superoperator that depended separately on TNS. Then this would be, in some quarters, this would be referred to as non-Markovian. The fact that there are two times here already kind of smells of there's some memory effect going on, because at time t, it also matters what happened at some earlier time s, let's say. So I think what your question was about was, why isn't this just a property of the system, right? And so from this perspective, you're looking at the map on the system. This lambda is what is happening to the system. But then you have to remember that where this came from was from its coupling to the bath. Right? And so this map inherits some feature that the bath has. The bath is in there. We can ask exactly what this lambda is, or what is the generator. So I wrote down what the generator was for Markovian dynamics. And so, for example, in the Markovian, in this case, in the Lindblad case, well, we wrote down somewhere over there, we wrote down what those cross operators were, and those cross operators, they inherit features from the bath. Right, so it's not so simple to decouple who is responsible. I take the view that the bath is responsible. The bath is the cause. The system sees the effects. The effect is captured by this map. The map displays features of Markovianity or non-Markovianity. For example, in this simple sense of a one parameter or two parameter semigroup. That's the effect that the system experiences. But what was the cause? The cause was whether the bath had memory or not. Umberto, did you want to add to that? Or Jenya?
So is it true to say that, okay, perhaps this is true, the pure state dynamics is Markovian. So if we have non-Markovianity, it comes from the system. It comes from the environment, because the pure state dynamic is always Markovian. Is it true?
You mean if a system starts out as pure and remains pure, then it's Markovian?
No, I mean just an isolated system, just pure dynamics.
An isolated system is certainly Markovian. That's true.
Okay, so if the dynamics is not Markovian, so it comes from the environment.
Yes, that's the cause. That's right.
Okay, thank you.
Hello, Mr. Lidar.
Yeah.
Can you hear me?
Yes.
Thank you for your great presentation. I have a question. The universal quantum computing is based on unitary gate and the unitary operator. But in the process of Markovian process, we have a non-unitary process because of the loss of information between the systems and the environment. I want to know how we can simulate this kind of dynamics and process of the open quantum system based on unitary operators in quantum computing. Is it possible? Can we decompose, for example, the equations and dynamics based on unitary operators?
Yeah, so the unitary operator is the one that goes into the expression that we need to evaluate in order to compute the cross operator. Right, so I'm not sure I totally understand what you're asking, but I think you're asking whether there's or let me say it this way. There are two ways for me to interpret your question. One is, is there a way to do everything in terms of unitary operators, describing open system dynamics using unitary operators? And the answer to that would be no, because open system dynamics is generally certainly not unitary. However, in general, to compute the cross operators, which is our starting point in a way, we need to know the unitary operator for the system and the bath. That is the U that sits here. We need to be able to calculate that if we want to do things from first principle. Then once we know this unitary, we can compute the cross operators, and we can compute the map, or we can compute Lindblad operators if we are willing to make a Markovian approximation. Does that answer your question, or did I miss it?
I want to know how we can simulate this process on universal quantum computing, the non-unitary process, because we know. Yeah, I want to know how we can simulate this kind of dynamics based on quantum computers.
Yeah. So simulation of open quantum systems using quantum computers, you can basically do in two different ways. One is you can try to design an algorithm that uses unitary transformations. Now I understand what you're asking about. That runs, let's say, on a gate model quantum computer. Another way to do it is you can try to use the naturally open system dynamics of any real quantum computer to mimic the open system dynamics of the system you're interested in. All right, so let's talk about the second approach for a second. The whole point of this lecture series, as Richard put it very nicely in the introduction, was the fact that we recognize that our actual quantum computers in the lab, they're never unitary. They're just not. They are open systems, right? So we know that they don't evolve according to the Schrödinger equation. They don't obey unitary dynamics. That's why we need this theory in the first place, to describe our real devices. So you can try to take advantage of that. You can ask, is it possible to construct a universal quantum simulator of open system dynamics using real hardware? Just like people asked in the earlier days of quantum computing, is it possible to construct a unitary quantum simulator, right, of arbitrary unitary dynamics? The answer to this unitary is yes. The answer to the can we construct a simulator using real hardware of arbitrary open system dynamics is more complicated, but in many cases the answer is still yes. And that's something that's been worked out. Now you were asking yet another variant of this, which was, suppose I wanted to use a unitary quantum computer, which doesn't exist in real life, but anyway, to simulate open quantum system dynamics. And the answer is, again, yes, because you can always take unitary dynamics and reduce it by making measurements, essentially, and make it simulate open systems in that way.
Thank you. Thank you.
Umberto, I think you were going to add something to my non-Markovianity comments.
Well, not much particularly. I think, yeah, I think the discussion so far was fine, for the amount of time we have.
Okay.
Can I ask a quick question?
Sure.
When you describe purity, purity is kind of classical ignorance, isn't it? When we decrease purity in our system. And can we also consider it as a measure for coherence or as a measure of decoherence? Or we should investigate other quantities like relative entropy of coherence or other quantities?
It is definitely not a good measure of coherence. And the reason you can see that is if you think precisely about what happens in spontaneous emission. So in spontaneous emission, let's say you start in a maximally mixed state. Okay, and now, so that is as classical a state as it gets, maximally mixed. And now you let spontaneous emission happen. Well, the purity is going to go up. Why? Because this system will decay to the ground state, which ultimately is a pure state when spontaneous emission is over, right? Everything is on the ground state. So now it's a pure state. So purity went up while coherence also well, coherence also went up. Sorry, there was no coherence was generated. The purity went up, but you started from some arbitrary state rho, and you went to the 0 state, which has no coherence, right? It's not a superposition. Coherence is a question about superpositions in a given basis. All right, so in this transformation from a general state rho, maybe you even started from, I said start from a maximally mixed state, but actually that's a bad example. Start from a superposition state. Start from a superposition of 0 plus 1. Right, so coherence now is high. Let's say C is coherence. Right, so coherence is 1 here. Coherence is 0 here, but purity is 1 here, and purity is 1 here. Right, so you see that they're not necessarily correlated. You can purify a system through decoherence.
Good example. I have another question that is when you write your Hamiltonian, it has 3-part system Hamiltonian, Bash Hamiltonian, and the interaction,
right.
HI. And when you said if we have a interaction Hamiltonian, we cannot write our unitary evolution operator as USB is not equal to US tensor UB. Okay,
right, right.
And in Lindblad master equation, usually people assume that the Born assumption, which is the separability of the system and Bass during time, not just initial state in all time. And I think there is a contradiction here because we always have interaction Hamiltonian between system and Bass, but we assume that separability, but we cannot write our kind of unitary evolution operator as a tensor product. I don't know. Is there any contradiction, or am I missing something? I don't know.
I think you're putting your finger on this the same discomfort that I tried to share with you about the separability assumption. And so I think what you're saying, if I understood you correctly, is how can there be a separable or a tensor product initial state when the interaction is always there?
Yes,
that's what you're saying, right? And yes, it's a very valid objection to have. It makes the tensor product initial state seem very artificial. How could it be a tensor product if there's always an interaction? Doesn't it mean that you have to be able to turn the interaction off at some point? So I share that discomfort with you. And in fact, I've done some work on what happens when you don't make this initial tensor product assumption. Do you still get meaningful quantum dynamics? And the answer is yes, but there are complications that arise. If you're not careful, you can't even write down a proper map from an initial reduced system state to a final reduced system state. And even the notion of a map becomes problematic without the assumption. There's a lot of work that was done on what's called quantum discord and so-called zero discord states. Turns out that there's a way to slightly relax the initial tensor product assumption. You can replace the initial system Bath state with a so-called zero discord state, and that is sufficient to also get a CP map. So we can get away with a little bit of correlation, if you like, but it's non-quantum correlation. Zero discord states have no quantum correlation. They have some classical correlation, essentially. It's a bit of a troubling feature of the theory of open quantum systems that we essentially have to assume no quantum correlation. Well, that's not totally true. We have to make assumptions or introduce restrictions in order to get a meaningful quantum map. Assumptions or restrictions, I'm referring to the initial system Bath state. And without those assumptions or restrictions on the initial system out state, then we can still get meaningful dynamics, but it's not as general as the cross representation, meaning it applies to a restricted set of initial states. So there are trade-offs there, and it's a bit of an uncomfortable situation that we're facing. But nevertheless, the theory works exquisitely well, and when you compare it with reality, it makes incredibly accurate predictions and so on. So we must be doing something right.
Thank you. Thank you for your answer.
So this is Anders. I have a question for you, a little more fundamental nature, maybe. Yeah. First, thank you very much for your lecture. It was very good. You briefly mentioned a maximally entangled state. I was wondering how you define that.
How do you define entangled or maximally entangled?
Maximally entangled.
Right. Well, rather than giving you a formal definition, let me just explain it by way of example. Right. So the simplest example is when you have two qubits, and let's say we write a state like this. Okay. So when A is equal to B, that's the maximally entangled case. When A is not equal to B, that is the not maximally entangled. So maximally entangled, more formally, you can provide a measure of entanglement. There are many different measures of entanglement, but they all tend to agree on when they peak, when they achieve a maximum. Right, so I don't want to get into measures of entanglement now, but you could do something like the Von entropy. And if you compute the Von entropy as a measure of entanglement, then you will find that the state when A is equal to B has the higher entanglement measure.
And how is this related to maximally mixed states?
Well, maximally mixed is the opposite extreme. So maximally mixed is very simple to define. That is just a classical coin, right? Or any classical distribution that is uniform would correspond to the maximally mixed state.
So that's when the purity achieves its minimum.
Correct.
Right. I was looking for a similar formula for the entanglement.
Yeah, purity and entanglement are not so simply connected. All of these are both pure states. It doesn't matter what A and B are, they're still pure states. So they have purity equal to 1, but they have different amounts of entanglement.
Right. So there is no simple formula. Like for the
there's no simple connection between purity and entanglement, but there is a simple formula for a measure of entanglement. So, okay, I mentioned the Von entropy, right? So the Von entropy, usually called S, is minus the trace. Minus the trace of rho log rho. And here rho is the reduced density matrix. So let's call this subsystem A, subsystem B. So let's say we trace out subsystem B from row AB. Let's say this is psi, and row AB is this pure state. Okay, A, B. So if you wanted to compute a proper measure of entanglement for this state, calculate the density matrix by this recipe, trace out B, plug it into this formula, and you got the measure of entanglement that is known as the Von entropy. And you will find that when coefficient A equals coefficient B, that measure is maximal.
Okay, thank you.
Hi there, if you can hear me, can I ask a question?
Yeah.
Hi, Daniel, it's Farhan.
Yeah.
My question was, it goes back to the to your previous answer that I don't know if the question makes a lot of sense formally, but is there a way we can actually say that a system is coherent if there are no quantum correlations at all? Like what I mean is there like a one-to-one correspondence between like coherence and quantum correlations, or is it just more complicated? Like, can you have a system which has no quantum correlations, but it's still coherent in some manner?
Yes, yes. So those are really two different things. So correlation is always between two different parts. Otherwise, the word correlation is not meaningful. So a correlation is there when you have at least two qubits, let's say. But coherence is well defined even for just one qubit. Right? So a qubit in the superposition state of 0 and 1, so a Schrodinger cat, is coherent, but it has no correlations with necessarily. It doesn't have to have correlations with anything. It's just a coherent superposition.
Yeah, but let's consider the 2-qubit case, for instance, right? Just
Okay.
should we know? Say we consider a 2-qubit case with, in one case where we clearly have quantum correlations, and in another where, say, we don't have quantum correlations. Can these 2 qubits still be in a coherent state if there are no quantum correlations?
If there are no quantum correlations between the 2 qubits, so you mean that they are, let's say that they're in a TensorFlow, right?
Yeah.
That would be a state with no quantum correlations. Well, each of the 2 qubits could still be coherent, right? So you can have qubit 1 could be in the superposition in a cat state, Schrodinger cat state. Qubit 2 could be in a Schrodinger cat state. And they are not correlated, but each is separately coherent, and therefore the whole state is coherent.
But so then maybe here the question gets, I guess, a bit complicated. So there isn't really a correspondence between correlation and coherence per se. It's just two different things.
Right.
But then what if you bring in classical correlations? Can you have, like, I don't know, 2 quantum states, which I don't even know if you can do that, but say you have 2 quantum states which are neither classically correlated, or like they're not correlated at all. They're like, I don't know, fully separable. Then again, like, I don't know, like, of course, then I don't know if you can, if you have 2 separable quantum states, how do you define coherence for these 2 separate states together? I don't know if you can do that, but yeah, it's just like, I'm not sure, because I think in the literature there's often this kind of confusion where if states aren't if there aren't quantum correlations, people kind of, I don't know, act as if it's not quantum enough per se. But I guess my point is, like, you can still have classical correlations and coherent phenomena without quantum correlation.
I think what you're trying to get at is whether, I mean, let's reformulate this in terms of something like quantum power. Okay, the power to solve computational problems. At least one of the last things you said made me think that this is what you're getting at. So, what makes a quantum computer powerful? Is it correlations? Is it coherence? Is it something else? Is that sort of what you're getting at?
Probably, but no. What I was really thinking about was like just coherent quantum phenomena, and the fact that often I think there are cases where you have strongly coherent quantum phenomena, so they are strongly quantum mechanical in nature, but you don't necessarily have things like quantum correlations in those systems, right? For instance, in very noisy quantum systems or very noisy quantum dynamics, or I don't know, systems where it's like imagine a chemical reaction, right? Modeling the quantum dynamics of any given chemical reaction. It's like it's always quantum coherent, right? Otherwise, the chemical reaction can't occur in principle. But again, this is a system where I don't think there's any guarantee of any correlation at all. maybe this but on the other hand, people are like people look at quantum correlations as a signature of quantumness, right? But my point is, I don't see how that applies to systems where you can have strongly quantum coherent phenomena, but not necessarily correlation of any form at all.
Well, I mean, as we established, coherence and quantum correlations are really two different things. The only thing I guess I want to add to that is that it is actually typically quantum correlations which are invoked in order to arrive at powerful quantum algorithms, ones that we think can solve problems that cannot be solved classically. Whereas coherence is, in that sense, is weaker, right? Because you can have a system that, or let's say a quantum circuit that keeps everything perfectly coherent, but never generates any quantum correlations, or more specifically, never generates any entanglement. So the circuit is, everything is coherent. It's a bunch of single qubits in superposition states. That will not solve any hard computational problem. If you want to solve hard computational problems, then you need to allow that circuit to generate quantum correlations or entanglement. Then it has a chance. So in that sense, coherence and correlations are qualitatively different. Whereas coherence is not powerful, correlations are powerful.
Yeah, that's actually, I would agree with that. And that's actually the conclusion I came to, thinking of it on my own. But then again, I don't know, there's, for instance, there's a kind of debate in atomistic spin dynamics at the moment where there's some code to classically simulate these spin dynamics, like for, I don't know, large systems approximately. What people did is they tried to actually look at the full quantum system, right, without approximations. And what happens is the code they had breaks down. And there's kind of this situation in the field where for atomistic spin dynamics, I think phenomena which are relevant to things like ultrafast magnetism and so on, physicists are kind of in a position, at least at the moment, where they have classical code which works, but when they try to apply this classical simulation codes and apply all the entire quantum system into these to solve these same things, it doesn't work anymore. Everything breaks down and you get wrong predictions. So essentially, I guess, I don't know, like for like comparatively huge large systems where I don't think it's like as clean to describe things as you can for things like qubits, like anymore. I don't know. It's just, I think the story is more complicated than just quantum correlations, right? Because quantum correlations are powerful when we have these engineered quantum systems, but I don't think it translates well to systems where, you know, like different systems, like where outside of quantum computation maybe, but maybe just other forms of quantum technologies.
Okay. Yeah, thanks for that comment. Do we have any other questions?
I have one quick question.
Yeah.
The way you defined coherence over here, it looks like the definition seems to be a basis dependent. For example, you said that,
yeah.
But I mean, can't I write zero state as superposition of plus and minus, and won't that be coherent state then?
Yeah, so you're absolutely right that coherence is a basis dependent quantity. Why is that so? Because in order to write a superposition state between, you know, one state and another, I must have chosen a basis, right? And so, so coherence is indeed basis dependent. And often people talk about decoherence as the decay of the off-diagonal elements of the density matrix and so on. And that's okay as a basis dependent notion of decoherence. But actually, one of the things I must admit I forgot to mention in my lecture was that we have a basis independent notion of decoherence. The way I like to define decoherence is whenever the dynamics is not unitary. Right? So when we have the cross representation with more than one cross operator, which forces the dynamics to be non-unitary, that is a scenario where you have decoherence. And that is a basis independent notion of decoherence. Likewise, if you write down the Lymphatic equation, and it has the first term, the commutator with the Hamiltonian, that part is responsible for the coherent dynamics, the unitary dynamics. But the second part, the part that involves the Lymphatic operators, once it's there, then we have decoherence. So again, this is a basis independent way to think about decoherence in Markovian dynamics. The presence of a non-zero dissipator term, this term that involves the Lymphatic operators. Right? So coherence is indeed defined relative to a basis. Decoherence we can define as any deviation from non-unitary dynamics, any deviation from unitary dynamics in a basis independent manner.
Okay, thank you.
Well, that might be a good place to stop. I hate to interrupt such fantastic discussion. So I thank all of you for your great interest in sticking around this long. It's a really great discussion. I'd like to thank Daniel for a fantastic day. This was really a great start off to the school. Quick announcement. So tomorrow, for those of you that are here, so tomorrow's lecture will be given starting at 8:30 Pacific Daylight Time by Christian Koch from Free University Berlin on the control of open quantum systems. And I think actually a lot of things that came up in the discussion today will be sort of followed up on in sort of, similar in different ways tomorrow by Christian. So I hope you will join us and join us for the rest of the week. I almost feel like I want to hand it back to Daniel and let him keep taking questions, but this might be a good time to end it for the day. So thank you, everybody. Thank you, Daniel.
Thank you for putting this together.
Yeah. Very good. Thank you all.
Thank you all.
Bye-bye.
Bye-bye.